In this video, we'll look at graphs of exponential functions. So again, we're beginning our exploration of exponential functions, and these are very useful in the real world. They happen to model many real-world phenomena. So in this particular video, we'll look at the graph of an exponential function. We'll start by remembering what an exponential function is, and then we'll go into plotting some points to get a sense of what the behavior of an exponential function is on the coordinate plane. And then we'll conclude with a quick reminder of how we can transform an exponential function. So recall that an exponential function is a function with base a defined for all reals as f of x equals a to the x, where a is strictly greater than 0 and a does not equal 1. Also recall from the last video, we put all of this together. We looked at f of x equals 2 to the x, and we looked at f of x equals 1/2 to the x. We found a few points for each of those just so we could start getting a sense of what those exponential function behavior is. So now we will plot those points. So we'll start with f of x equals 2 to the x. So at 0, we said that it went through 1. 2 squares up will be 1. At x equals 1, it goes through 2. At x equals 2, it goes through 2, 3, 4. At x equals -1, we have 1/2. And at x equals -2, we have 1/4. So our exponential function f of x equals 2 to the x looks something like this. And then similarly, for f of x equals 1/2 to the x, at x equals 0, we had y equals 1. At x equals 1, we have y equals 1/2. X equals 2, we have y equals 1/4. And then if we go to -1, we have y equals 4. If we go to -1, we have y equals 2. And then if we go to -2, we have y equals 4. So then the graph of our g of x, exponential function with base 1/2, looks something like this. So now a couple things you might notice. One, you might notice that as we go to -infinity for f of x, we just keep getting closer and closer to the x-axis. We never quite hit it. And that should make sense intuitively. If we have 2 to the negative something big, that gives us 1 over 2 to the something big, which as 2 to the something big is really, really large, that goes to 0. Right, so that intuitively should make sense that we have this horizontal asymptote here for our f of x equals 2 to the x. And similarly, if we have 1/2 to the something positive big, that's 1 over 2 to the big number, which that also goes to 0. So for both of these exponential functions, they have an asymptote at the line y equals 0 for the x-axis. Also, you may notice that both of these go through the point 0, 1. You may also notice that the domain of both of these graphs is all real numbers. And the range is the set of outputs 0 to infinity, excluding 0, right? Because we can get infinitesimally close to 0, but never quite get there. And then so some terminology. We might call exponential functions of the base greater than 1. We might call these exponential growth functions. And for exponential functions with a base between 0 and 1, we might call those exponential decay. And that terminology comes in handy when we're looking at applications of exponential functions. So for graphs of exponential functions, the exponential function f of x equals a to the x for a greater than 0 and a not equal to 1 has domain all real numbers and range 0 to infinity excluding 0. The line y equals 0, or the x-axis, is a horizontal asymptote of f. And the graph of f has one of the following shapes. For a greater than 1, we start really, really small off towards -infinity. We get a little bit bigger, and then once we hit 0, we take on the output 1, and then we get really, really large really, really quickly. Exponential growth functions get really big really quickly. And then for a between 0 and 1. In the negative infinity direction, we start up way towards positive infinity, and then we get smaller quickly as we approach 0. Once we hit 0, we take on the value 1, and then as we leave 0, we get infinitesimally close to the horizontal axis, the x-axis, the line y equals 0. And of course, we may transform our exponential functions. If our base exponential function looks something like f of x equals a to the x, then a constant in front of the base function will cause the function to stretch vertically or shrink vertically. So for b greater than 1, we'll stretch up, and for b between 0 and 1, we'll shrink down towards the x-axis. And of course, if we have a negative b, that will flip over x-axis. Our c determines the horizontal shift. If c is positive, in other words, if we have an x minus c inside our base function, then we shift to the right. If c is negative, then, in other words, we have an x plus c inside of our base function, we shift to the left. If we have a negative x inside, so a negative x flips over the y-axis. And then, of course, we have a vertical shift with adding a constant outside of the base function. If we have a positive d, we shift up. If we have a negative d, we shift down. So these are things that you can look for as we begin to graph more exponential functions, identify how each of the numbers affect the base function, start with the base function, and then move around from there.